Okay, so in the last video we talked about momentum, and remember that the symbol for momentum is a p, and momentum is mass times velocity. Okay, and so what we're going to see in this next part of the unit is that there's a lot of different situations where we want to calculate the change in momentum of an object. Okay, so change in science has a specific meaning, and usually we write change in using the Greek letter delta, which looks like a triangle. And so if I want to write change in momentum, I would write delta p. Okay, so the delta means change in, and the p means momentum. Now, anytime in math or science when you have a delta, it always represents change in, and that always means the final value minus the initial value. In other words, what I'm saying is that change in momentum, because momentum is mass times velocity, if an object is changing its momentum, that would be the mass times the final velocity minus the mass times the initial velocity. Okay, so change in anything is always a final value minus the initial value. So mv final would be the final momentum, and then mv initial would be the initial momentum. Okay, and so you see this in situations where an object is either, speeding up or slowing down typically. Okay, so we're going to start off doing some basic calculations with change in momentum. Alright, so pause there, make sure you have that in your notes, and then we will move on. Okay, so take a look at example 3. So example 3 says a 60 kilogram skateboarder. Right away I identify the mass of the skateboarder. Traveling at 4 meters per second, runs into some gravel and slows down to 1.5 meters per second. Now, one of these velocities is going to be the initial velocity and one is going to be the final. And so you have to think which comes first. Well, first the skateboarder is traveling at 4 meters per second, and then he slows down to 1.5 meters per second. That means I'm going to label this 4 meters per second. I'm going to label that VI. And the other one I'm going to label VF. Now when the question says calculate the change in momentum is delta P, and change in momentum is the final momentum minus the initial momentum. So that would be mv final minus mv initial. And now I just need to plug in some values. Okay, so the mass is 60. The final the final velocity is 1.5 meters per second. And then I'm going to subtract m times vi, so 60 times the initial velocity, which was 4. And then I'm just going to simplify that. Okay, so 60 times 1.5 is 90, minus 60 times 4 is 240. And so if I subtract those two things from each other, I get negative 150. And the unit for change in momentum is kilogram meters per second. Okay, so the change in momentum of the skateboarder is negative 150 kilogram meters per second. Notice, by the way, the negative sign in this case indicates that the skateboarder is slowing down. Okay, so that's why the change in momentum is negative. So pause it there if you need to look at that some more. Okay, example 4. Example 4 says a 1.5 kilogram toy car. Right off the bat I see that's the mass of the toy car. Travels at 5 meters per second and runs into a wall. What is the change in momentum? So once again, I'm asked for change in momentum, delta P, of the toy car after it crashes. Now, at first glance, it looks like we don't have enough information because we only see one velocity. But you have to use some context clues here. If the toy car is running into a wall and crashing, then that's a context clue telling you that the car is going to stop after it hits the wall. In other words, the final velocity of the car is going to be 0 meters per second. That means that this 5 up here has to be the initial velocity. So the initial velocity of the car is 5 meters per second, and once it hits the wall and it stops, the final velocity will be 0. So you have to use your context clue to figure that out. Now to calculate change in momentum, of course, that would just be mv final minus mv initial. And from here, it's just a matter of plugging in the values I have. I know the mass is 1.5, v final is 0, minus the mass, which is 1.5, times v initial, which is 5. And if I simplify that out, 1.5 times 0 is 0, minus 1.5 times 5, which is 7.5. And so I find that the change in momentum of the toy car is negative 7.5 kilogram meters per second. And the unit for change in momentum is kilogram meters per second. Okay, so that is example 4. Okay, so pause it there if you need to look at that some more. Okay, so now we're going to see what we can do with this change in momentum. And so that brings us to something called impulse. Now going back a couple units, we know that if an object's velocity is changing, there must be a net force acting on that object. Okay, and so since momentum is mass times velocity, if you have an object change its velocity, that means it's also changing its momentum. Okay, now we call this change in momentum impulse. Okay, so in other words, in order for an object to change its momentum, it must experience what's called an impulse. Now, a couple important things. Number one, it's very important that you understand, because this is not going to be given to you, that when we talk about an impulse, we're talking about the exact same thing as change in momentum. Okay, so impulse and change in momentum are equal to each other. Okay, however, each one of them has its own equation. So in the past few slides, we did calculations with delta P, where that's just mv final minus mv initial. Impulse also has its own equation. So the symbol for impulse is a capital I, and the equation for impulse, we write F times delta T. Okay, now F is the symbol for force. Delta T, that's all one thing. It's not delta times T. It's all one thing. This is a specific time. This delta T is the time that the force is acting for. So delta T is how long the force is acting for. Let me give you an example. Let's say somebody throws a baseball at you. You're playing baseball. They pitch the ball to you. You swing your bat. Okay, the bat hits the ball. As the bat hits the ball, there's going to be an impulse. Delta T in that case would be the time that the bat is touching the ball. Now, when you hit a ball, of course, that happens very, very quickly. And so in that case, delta T would be like really small, like, way less than a second, because it happens in an instant. So delta T could be a really small time. It could also be a really big time. Okay, so for example, if you're like pushing it, let's say your car breaks down, you try to push your car up the hill, and you push your car for 2 minutes trying to get it up the hill. Well, in that case, delta T would be 2 minutes, okay, because that's how long the force is acting for. So delta T is just represents how long the force is acting for. F represents the force, and if you multiply those two together, you get impulse, which is the same as change in momentum. Okay, and so sometimes you'll be asked to calculate the impulse, but what it's actually asking you to find is the change in momentum. So you need to understand that those two are the same. Because I will give you the change in momentum equation, and I will give you the impulse equation, but I won't tell you that those two are the same thing. That's just something that you need to know on your own. Okay, so impulse is equal to change in momentum. Okay, let's do some more examples. Okay, so example 4.25. Okay, so example 4.25 says a baseball player swings at a fastball and strikes the ball with his bat. If the bat applies a force of 750 newtons on the ball and is in contact with the ball, I'm missing a word there, it should say is in contact with the ball for 0.5 seconds, calculate the impulse on the ball and calculate the change in momentum of the ball. Okay, so as I'm identifying my givens, I see here that I have a force. So 750 newtons, that is the force from the ball. Now remember, in the equation, delta t is the time that the force is acting. So when it says that the bat is touching the ball for 0.5 seconds, that's half a second, that is your delta t. Now, as you're looking at your equations, you see the equation for impulse is I equals F times delta t. And so that makes it very easy to calculate the impulse. That would just be the force, which is 750, times delta t, which is 0.5. And then if you multiply those two together, you get 750. The unit for impulse, because you're multiplying force by time, force is in newtons and time is in seconds. The unit for impulse is Newton seconds. NS, Newton seconds. Not newtons per second, Newton seconds. Okay, so I would say the impulse here is 375 Newton seconds. Now, the second question says calculate the change in momentum of the ball. But I don't have to use my delta P equation because I already know that impulse and change in momentum are the same thing. So this is kind of a trick question to get you to realize that impulse and change in momentum are the same. That means the change in momentum of the ball is also 375 because they're the same thing. I'm just going to change the units, but the numbers are equal to each other. Okay, so impulse and change in momentum are the same thing. Okay, so pause there if you need to look at example 4.25 some more. Okay, so let's try example 4.5. It says a girl playing pool takes a shot at a 0.2 kilogram pool ball. Right away I see I've got mass right there. That is rolling towards her at 0.5 meters per second. Okay, so I'm going to label this VI for the initial velocity. I know this is the initial one, by the way, because I know she's about to hit the ball, so that's how fast it's moving before she hits the ball. And so after she hits the ball, it's going to roll backwards at 1.2 meters per second. Now this is really important. You need to understand that if it's rolling towards her and then she hits it backwards, that means the new velocity should actually be negative because it's going in the opposite direction. Okay, so if it's coming towards her with a positive velocity, when it goes away from her, it has to have a negative velocity. Now the first question says calculate the change in momentum of the ball. So change in momentum is just mv final minus mv initial. And so that would be the mass, which is 0.2, times the final velocity of negative 1.2 meters per second. And then I'm going to do minus the mass times v initial. So minus 0.2 times 0.5. And so I'm going to find delta P, the change in momentum. I'm going to put this in my calculator. I'm going to simplify that. I'm going to get negative 0.24 minus 0.1, and that reduces down to negative 0.34 kilogram meters per second. And so the change in momentum of the pool ball is negative 0.34 kilogram meters per second. Now the next question says calculate the impulse of the pool ball. Of course, impulse and change in momentum are the same. Okay, so the impulse I can say right away is going to be negative 0.34 Newton seconds. If her pool stick is in contact with the ball for 0.05 seconds, calculate the force on the ball. So now, for the first time, I'm combining my two sets of equations. Because now I'm given delta t, they're asking me for the force. I know that the impulse equation is I equals F delta T. And I know what I is because that's equal to the change in momentum that I just found. So I is going to be negative 0.34. I'm asked to find the force. And then delta T here is 0.05 seconds. Because when you hit a pull ball, it happens really fast. Right? So to get F by itself, I need to divide both sides by 0.05. And so I'm going to go to my calculator. I'm going to do 0.34 divided by 0.05. And I'm going to get negative 6.8 newtons. And so that is the force that acts on the pull ball. Okay, so with example 4.5, you're starting to see how the change in momentum equation and the impulse equation can work together because impulse and change in momentum are equal to each other. Okay, so pause it there and look at that some more. Okay, so the very last thing I'm going to talk about really quickly is example 5. Okay, example 5 says Mr. Walker, who has a mass of 80 kilograms, jumps off a table. Before he lands, he has a velocity of negative 5 meters per second. And the first question says calculate the impulse, aka the change in momentum of Mr. Walker when he lands. And normally I would actually do this in class for you guys, but it's hard to do that remotely. Okay, so I have my mass. I actually need to lose some weight this year so I can get that mass down. Before I land, I have a velocity of negative 5 meters per second. Now you might think that's the final velocity because that's after I jump off the table, but this is actually the initial velocity because what's going to happen is I'm going to land on the ground and then eventually I'm going to stop. Right? That's what happens when you land on the ground, right? You stop. And so that means my final velocity is actually going to be 0 meters per second. And so if I want to calculate the change in momentum, delta P, I'm going to do mv final minus mv initial. That would be 80 times 0 minus 80 times negative 5. I'm going to write this up here. And so that means my change in momentum is going to be 0 minus negative 400, because 80 times 5 is 400. Okay, so my change in momentum is actually going to be positive 400 kilogram meters per second. It's going to be positive because when you subtract a negative, you get a positive value. So my change in momentum is going to be positive 400 kilogram meters per second. Now, it's important that you understand that is going to be the same no matter how I land. Okay? Because in the next two questions, it asks me, what's the force on my legs if I land in this time? What's the force on my legs if I land in this time? In both of these situations, my change in momentum is a fixed number. Because my final velocity can't change. It has to be 0 because I'm going to stop. My initial velocity is also fixed because that just depends on the height of the table I'm jumping off of. Okay, so for these next two questions where I'm solving for force, my delta P is going to be the same in both of those cases. Now, these two questions are both asking me for force, and they both give me a different time. Okay, and remember, impulse is the same as change in momentum. So if my change in momentum is 400, that means my impulse is also 400 Newton seconds. And so I want you to try to use the impulse equation, I equals F delta T. I want you to find the force on my legs if I land in 0.1 seconds, and the force on my legs if I land in 0.02 seconds. Okay, so if I land in 0.1 seconds, I have I equals 400. I'm solving for force. if delta t is 0.1 seconds, then F would be 400 divided by 0.1, which is 4,000 newtons. Okay, so the force on my legs if I land in 0.1 seconds is 4,000 newtons, which sounds like a lot, but it could be a lot higher. Okay, so hopefully you got 4,000 newtons for the first one. For the second one, using the same impulse equation, I have the same impulse, that's 400, but now when I go to find the force for the second one, I'm going to plug in 0.02 seconds for the time. So now F is going to be 400 divided by 0.02, and so I'm going to plug that into my calculator, 400 divided by 0.02, and I'm going to get 20,000 newtons. Alright, and so that's the force on my legs if I land in less time. So notice if I land in a shorter amount of time, the force on my legs is actually bigger. And you might ask, like, how do you change the time that it takes to land? Well, what you should do when you land on the ground is you should bend your knees. Okay, next time you jump off of something, when you hit the ground, notice you bend your knees, or you might even do like a roll, like a ninja roll or something. And the reason you bend your knees when you land, you don't lock your legs when you're landing on the ground. That's bad. You want to bend your knees because you want to increase the time that it takes your body to stop. Okay, the longer it takes your body to stop, the lower the force is on your body. Okay, so if I want to decrease the force on my legs because I don't want to injure myself, I want to bend my knees as much as possible. And if you've ever watched people that do martial arts or people that do gymnastics, they tumble and they roll when they jump off of things, and the reason that they roll is because that's increasing the time that it takes them to stop. That decreases the force on their body. Okay, and so this is one of the applications of impulse and momentum. Okay, so pause it there, and make sure you have this in your notes and you understand all of this. I just want to talk about this for one more minute. Okay, so in other words, what I'm saying is that in the situation we saw before, we had the same impulse, but when you had the same impulse over a bigger time, you have a smaller force. And when you have that impulse over a shorter time, you have a bigger force. So like when you throw an egg at the wall, when the egg hits the wall, it's going to stop very quickly. And so that means the time is going to be small. That means the force on the egg is going to be really big and the egg's going to break. Whereas let's say somebody's holding up like a bed sheet. If you throw the egg at a bed sheet, the egg might not break. Because when it hits the bed sheet is like soft and it has some give to it, and so that means it takes the egg longer to stop. So more time to stop means less force on the egg. That means the egg might not break. Okay, and so that's one of the applications of momentum and impulse. Okay, and the other real life application of that, by the way, is airbags. This is how airbags save your life. So when you're in a car crash, what happens is the airbag comes out, and instead of hitting your steering wheel and stopping really quickly, you hit the airbag, and the airbag takes longer. It takes your face and your body longer to stop, and because of that extra time, that decreases the force on your body and protects you from injury. And you still might get injured from the airbag, but you won't get as injured because it took you longer to stop, so there was less force on you. Okay, so that is one of the awesome applications of impulse and momentum. Okay, so that is it for this section of the unit. As always, please let me know if you have any questions, and I'll see you guys in the next video.